welcome to CS 1401 video 19.2. In this video, I'll discuss implementation of 4 recursive algorithms that we've already implemented in Java: countdown, factorial, Fibonacci, and sum digits. This will help illuminate the similarities and differences between programming in Prolog and programming in Java. I'll start with countdown. You'll remember that this simple program takes one integer argument and prints the numbers from that number to 0, one line at a time. Remember that every recursive algorithm will have at least one base case and at least one recursive case. For countdown, the base case is when the algorithm's argument reaches 0. That's the last number we want to print. The recursive case is if the algorithm's argument is greater than 0. We'll want to print that number, then print the numbers less than that number. Here's my Prolog code for the algorithm. The first clause of countdown is the base case. If the argument is 0, we've reached the end, and we just do write line 0 and return true effectively. The other clause is the recursive case. If the number isn't 0, we'll call it n. Now, we'll want to make sure that n is greater than 0 so that we don't have a negative argument and recurse forever, trying to go below 0. Well, if n is greater than 0, then we write it. We decrement n and put that value in the variable next, and then recursively call countdown of next. Let's try it out for countdown of 5. And we get exactly the result we were expecting. By the way, this code seems to have an extra statement in it. After the program prints the current number, it has the statement next is n-1. Why, instead of doing this and then calling countdown of next, can't I just call countdown of n-1 directly? To find out, I have a second version of the program called countdown2 that does exactly that. Let's try it out. Wow! What's happening is that the arithmetic expression is being passed as the term's argument. In the original version, the is operator evaluated the arithmetic expression, and I used that for the recursive call. So to get programs like countdown to work the way we want them to, we'll use is so that arithmetic expressions get evaluated. Next, let's look at factorial. Recall that factorial of n calculates the product of the numbers from 1 to n. By convention, factorial of 0 is 1. So the base case will be factorial of 0, and the recursive case will be factorial of n greater than 0. Here's my Prolog implementation of factorial. The base case is that n equals 0, in which case the second argument will be the result, that is factorial of 0, which is 1. In the recursive case, for argument n, we'll want to bind the second argument f to the result of factorial of n. We'll check to make sure that n is greater than 0. We'll decrement n, that'll be useful for factorial of n-1, and bind variable n1 to that value. We'll calculate factorial of n1, which is n-1, and that result will be called f1. Now we're ready to calculate factorial. F is n times the factorial of n-1, which is the value f1. Let's try running it. Well, the factorial of 0 works. Let's try it for a larger number. And that's correct too. Next, let's look at Fibonacci. This will be the inefficient recursive algorithm, but it will still help compare Prolog and Java implementations of the algorithm. There are 2 base cases. First, fib of 0 is 0, and fib of 1 is 1. If the argument to fib is greater than 1, well, we'll call it n, and we'll bind f to the value of the Fibonacci function. Well, to calculate f, we're going to need to calculate Fibonacci of n minus 1 and n minus 2. First, I'll bind n1 to the value of n minus 1, and I'll bind n2 to the value of n minus 2. Now I can calculate recursively fib of n minus 1, which I'll call f1, and fib of n minus 2, which I'll call f2. And finally, I can calculate f, which is f1 plus f2. Let's try it out. First, we'll try the base cases. That works. And that works too. Now let's try fib for a bigger value. That's correct. And now let's try fib of 6. And that's right also. Finally, let's look at sum digits. You'll recall that this algorithm takes an integer and returns the sum of the integer's digits. For example, sum digits of 215 would return 8. Here's the pseudocode algorithm I presented when I implemented sum digits in Java. The algorithm sum digits takes a single argument, which I'll call the number. If the number is less than 10, then I return the number. Otherwise, I return the number mod 10, which is the last digit, plus sum digits of the number div 10, which will be the digits to the left. The Prolog implementation follows the pseudocode directly. Just like in the pseudocode, in Prolog the base case is when the argument is less than 10, in which case we'll want to return that single digit. The recursive case is when n is greater than 9. That means there's more than one digit. I'll bind n mod 10 to the value of n mod 10, and I'll bind n div 10 to the value of n div 10. And now I'm ready to make the recursive call. I'll call sum digits of n div 10, that's the digits to the left of the current digit, and calling sum digits of n div 10 will bind st to the sum of the other digits. Finally, I'll add n mod 10, which is the final digit, plus the sum of the previous digits, and set s equal to that, and that's the value that will be instantiated in the second argument of sum digits. Let's try it out. First with a base case. That works. Now let's try it with our example. And that works too. So that's a look at implementing Prolog in 4 of the algorithms that we've already implemented in Java. Arithmetic is relatively easy in Java, and that's a reason why students learning computer science who start programming in Java tend to see a lot of arithmetic programs. Arithmetic in Prolog is somewhat more tedious, mainly because of having to evaluate arithmetic expressions with is. But Prolog really shines in handling lists, and in videos 20.1 and 20.2, I'll explore some fun and elegant recursive programs for lists. See you then.